Hello, this is Dr. Mantesh. In this tutorial, we will try to take second experiment, that is for the Booth multiplier. So we are supposed to write Verilog code, testbench, and do the same thing as we did the maximum delay and critical path for the previous experiments. Okay. It's good to take a background of the experiment, how exactly it works. I'll take 2 minutes. So actually it's Radix 2 4-bit Booth multiplier. It's a signed multiplier. Okay, so first MSB will be considered as sign, and if it is a signed bit, that means if MSB is 1, the remaining bits will have 2's complement of a number. Together they constitute, 4 bits constitute a negative number. So these are the basics. This is a block diagram or architecture of Booth multiplier. So A is one operand, and together we have Q is another operand. However, P and this A and Q together will give result, that is P 8-bit, maximum of 8-bit. So mod 4 counter will be there. We'll try to, because it is 4-bit, it is trying to do that. Counter, okay, it checks for 4 times. The iterations, number of iterations will be 4 times. So looking into the flowchart of the Booth multiplier, if A is 0, let me take an example first so that we can. So you would like to multiply 7 and 3, both positive. So 7 indicated something like this, 3 is indicated something like this, 0, 111, 0, 0, 1, 1. Then the first operand is stored in M, second operand is stored in Q, and initially A will be 0 and Q, previous state of Q is Q of 1, the first bit of Q is 0. Next thing, suppose if you load, so initial value of this thing is 0 and Q and these are initial values. Okay, this is from this value. If it is 1, 0, if Q and Q of minus 1 is 0, then it will take, okay, this path, A is equal to A minus M. If it is 0, 1, Q 0 and Q minus 1, if it is 0, 1, it is going to be A is equal to A plus M. In 1, 1 and 0, 0 case, in these two cases, it will simply shift. There is no add or subtract. Just remember these things. And then after doing this, A is equal to A minus M, because it is 1 and 0, then A is equal to A minus M, 0 minus 111 will be, that means you need to do 2's complement addition. Then you will get A is equal to A minus M, because A is smaller, M is bigger, so you are supposed to do that 2's complement addition to get subtraction. Q value will be same during that period. So this completes one iteration. So similar to that, we have to do another 3 iterations. Next one, we are supposed to shift it. In any case, we should shift. This is that 4 counts what I was talking about. Then once it is shifted to right, we will get this A value will be, this 1 will come here, Q value will be shift right, no? So this is going here. Also it is arithmetic shift, so this MSB will be preserved, that we should remember. Next one, see, the shifting is together. We should remember this block diagram. Shifting is together, so A content will also move to Q. This A content is moved to Q, and since it is arithmetic shift, this one will continue to appear because it is a sign bit. And then this Q is moved here, this one is moving there. So just remember, it is concatenation of these two and shifting together. So shift, similar to that, if it is 1 1, what to do? Simply shift. If it is 0 1, E is equal to A plus M. If it is 0 0, only shift. So these are the things, and that finally we are going to get the output as 21. 7 into 3, 7 into 3, 21. So we are trying to do the same thing in this experiment. Let's go back and check Xilinx. What are the steps to be followed? File, new project. I'm giving it as Booth Multiplier, something like that. Give some description, which is very much useful. I'll try to keep the same hardware. Make sure that you have Verilog here. Then summary of the project. Okay, once you do this, we know that we are supposed to go for new source, project new source, or the shortcut is here. Take Verilog module, Booth Mul, give some meaningful name, the inputs of those things. However, I already told that I have ready-made file. I don't want to give anything here. I have a code. I am simply going to copy and paste. So let me go to code. Both okay, this is the code. Same thing what all explained there, it is written here. You can see if it is 0 and if it is 0 0 0 1 1 1 1 0, what to do? So it is, I am going to simply copy paste the code. Control A, Control V. Suppose if you don't know commands, what I did, I just select all. Select all, Control A. I just delete it and then paste. Okay, Control S or save. I just added it to this is called as project window, process window. This is visible for coding. This is called as console. Now if I try to simulate without also, I already told it is possible without test bench also. If you are unable to write the test bench, still you can able to do the simulation. Going to behavioral model. In the process window, just I am repeating what I did. Suppose if you try to simulate, you will be in this initially, in the synthesis process or implementation. Come to simulation. Suppose if selection is not proper, you don't get the option. So you should be selecting the top model, then simulate behavioral model. Okay, I would like to give, if you want, you can give clock as well, clock, post clock. So all these things are possible, as I already told. 10 nanosecond. So you can give, instead of that, simply you can write a what I say, test bench. Okay, that is a good thing. Even the curriculum says write a test bench to verify functionality of the Booth Multiplier. So I'm not going to do it. If you want, you can do it, load, and one time you reset and then it will become 0. Okay, then run. Once you do that, then you load force constant 1, then you give M and Q. What we were giving is 7 and 3. Unsigned, sorry, it is signed decimal. 7, force constant 3. Once you do that, if you run it, you should be able to getting the output in the P. Then Radix unsigned decimal. Okay, so you will get initial values. I have not given, I think. Q minus 1 must be 0 initial value. Reset is after loading. So where is the result? It is in P, force constant, Radix, signed decimal. Give me a second. Then I think I must make this as 0 or else it will not do its job. Wait, I think we didn't do this. Okay, let me restart this. And then what we are trying to do is first give the clock, force clock 0, 1. Here I'll give 250 nanosecond. I just want 4 or 5 clocks in 1 microsecond. That is 1 microsecond is 1000 nanosecond. So 250 nanosecond period means you will get 4 clocks. Next one, let it be 0 first. Force constant 0, and then we'll reset this initially. Okay, let me reset. So we'll get all the, as soon as you reset, this count will be initialized to 4, and then we'll give inputs. Our inputs are M is 0,111, that is 7, and Q, that is second operand, is 0011, that is 3. Then what we are supposed to do is load this time, force constant, load. Also we don't want this to be reset, so let me make reset as 0, apply. Okay, if I run this now, the data is loaded. Here it is, these are the things that are loaded, just loaded, no output yet. Then to get the output, what we are supposed to do, force constant load. So you have to make load as 0. Then if you run this time, we will get output, okay, in 4 clocks. So let me go and zoom it, what we are getting. So this one is output, that is, we'll go as Radix unsigned decimal, that is 21. Sorry, Radix signed decimal, this is signed number. Radix sign decimal. So 7 into 3 is 21. This is how you are supposed to check the output. Suppose if you want to load another value like okay, we'll see it in the test bench, because in the test bench you would like to give one negative input and just check whether it works or not. So this is how you can able to simulate and verify the functionality without writing test bench. To do this, you should have a lot of knowledge about what you have written in the program, because I have read each and every line of the code, so I know this clearly what is happening, so I have given accordingly. So we'll stop at this point. We'll take test bench. Okay, let me open a test bench. Okay, it is there in the, so I don't have to worry. I'll just if you have already, you can add it from this test bench. This is not supposed to be test bench because it is VHD. By default, I think by mistake I have created this. I'll just remove it. Add. Okay. So it is there in the PDF itself. So I'll share this PDF with you now. I'll just take this as it is. I'll take new source, Verilog module. I'm trying to paste. Then I think this will give us okay, few more lines are there, I think, end and clock. So this is the waveform in Cadence. This is how you're supposed to give a constraints file, that is the C file. We are giving constraints in the Cadence, but in this tutorial we are trying to show only with respect to Xilinx. So I'll just save it. So now it is added. Okay. So now you are in simulation. If there are any errors, you can check it. Behavioral check syntax, then simulate. The code is simple, self-explanatory, you don't have to worry. So after running, you just click on default and view all, zoom to full view. So whatever I did, it is also doing the same thing. You can see what is M. What I do, I'll take it up, 2 operands first and then output. I'll make it signed. It is -6 and 4. So 6 4s are 24. Since it is -6, it is -24. So this is the correct answer. Okay. Though initially you think it is not the answer, since it is -6, it is going to be the answer. These things you can take it to your screenshots for record. You can take print screen. I just hit print screen in my keyboard. Go to paint. Paste it here. Right click, invert color, crop as much as you want. Copy. You can take it to any of your this thing. You can copy it to Word file. I just close now. In the Word file you can simply paste it. So this is all about Booth Multiplier simulation. The second thing what we are supposed to do is remove this test bench and synthesize this design. Blank document. So if you paste it here, so your waveform is ready. After 4 or 5 waveforms you can take up single print and paste it or keep it for reference. So once you do the synthesis, go to summary and you can check this is the number of cells. Okay, what they mentioned, what they asked in the, so total number of cells, okay, in the synthesis. Okay, I don't want this as well. The total number of cells, you can note it down. You can directly write the same table. If you want to see the maximum path delay or critical path delay, you can see the synthesis report. Okay, the critical path starts from count to 2 and ends at A0. This is the critical path. You can write it. Also, the maximum delay is 6.62. As I already told, this depends on the speed grade as well. If I take speed grade as 4 or any other device, for example, if I take PQ, one more device that we had, if you synthesize, now it is 6.62 nanosecond, it will reduce or it may increase. Probably it will reduce now. So I'll go back and check what is the critical path delay. See, now it has increased because I have changed from PQ208, which is small device, to big device. XC3S50 was there earlier, now it is XC3S200. From speed grade 5 I reduced it to speed grade 4. So from 2.5 nanosecond it became 7.75. This is all about setting the constraints. If they ask, you can do this. Okay, data path, critical path, as they mentioned, starting point count to 2 is. So this is the critical path. I'll highlight it. This is the critical path. And maximum delay is 7.75 for this device. 7.75 nanosecond. You can also see the static power as I have already shown. You can expand implement design and go to place and route, analyze power, but it shows static power as I already told, because the design is too small. The Xilinx Expt analyzer, the starting point of power is 1 milliwatt. If it is below that, it will not show. However, if you see cadence, it will give, in microwatt as well. So I do not have screenshot at this point. So I'll stop this. So the dynamic power is 0 because it is too small. The leakage is 0.041, that is 41 milliampere. This is static power. Okay. So this is all about experiment number 2. Hope you understood. See you.